here, find the exact global maximum and minimum values of the function. The domain is all real numbers unless otherwise specified, and we are giving this function g of x. So now this is an open function and we want to find the global maximum and minimum. So first step gonna be finding the critical points. A critical point gonna be when we have the first derivative is 0 and undefined. The first derivative is 4 minus 2x. Notice this is defined on all real numbers or all x values. So move to the next step, which is where's the first derivative is 0. It's gonna be 0 when x equal to 4 over 2, which is 2. Now notice 2, it's in our domain, which is all real numbers. Therefore, it's considered to be a critical point. The second step, we're gonna evaluate the critical point in the function g of x. So the value of the critical point in the function is -1. So the third step gonna be determine the critical point. Is it a local maximum or is it a local minimum? So that we can do the first derivative test or the second derivative test. Here I choose to do the first derivative test. So I draw the x-axis and then I mark our critical point, and then I want to know the signs of the first derivative when it's larger than our critical point and when it's lower than our critical point. Here I just select these numbers. I select these numbers randomly. So I select 3 and 0, and then I'm going to evaluate them again in the first derivative. Here, what do I care about is the signs of the first derivative evaluated at these points. Now, what I'm gonna do, I'm gonna take these signs and then I'm gonna mark them on our x-axis. So first, at when it's lower than our critical point, it's positive. When it's higher, it's negative. So our function g of x is going down. It's going up actually on the left, and then on the right of our critical point, it's going down. Therefore, from this shape, we can notice that our critical point is a local maximum. Now, the fourth step is to determine what's the behavior of the function f of x and the endpoints. So notice the function is a downward facing parabola. So remember, at x equal to 2, we have a local maximum. And then here on the right, as x goes to infinity, the function g of x is going to minus infinity. And then on the left, as x going to minus infinity, the function g of x is going also to minus infinity. Now we can also do this using the function g of x. So as x go to infinity, gonna be 4, and then to infinity minus infinity square minus 5. Minus 5 is just a constant, so we don't care about this part. So notice that infinity squared is faster than the first term for infinity. Therefore, this is gonna be going to minus infinity. And then when x going to minus infinity, now notice that the first two terms are negative, but also the second term is faster. Therefore, when x going to minus infinity, the function also going to minus infinity. So what does that tell us? It tells us that at x equal to 2, we have a global maximum. but we don't have a global minimum since the function and both ends are decreasing in value. Now, for part 2, we have this function f of t equal to t over 1 plus t squared. First, we will have to find the critical point is where the first derivative is 0 or undefined. So, notice here, this is a rational function, which means to take the derivative, we're gonna use the quotient rule. So I'm gonna assign the top t to u and the bottom 1 plus t squared to v. Now I'm gonna take the derivative of u and v. Now we are ready to apply the quotient rule. Gonna be 1 plus t squared minus t multiplied by 2t, and then all over 1 plus t squared, and then all squared. Now I can simplify the top. Notice on the top we have smaller terms, t squared, so I can subtract these. Now this is the first derivative function. Now notice where the first derivative is undefined. It's when we have 1 minus t squared over 0. So the bottom is assigned to be 0. Now when that gonna be? It's going to be when 1 plus t squared equal to 0. And notice 1 plus t squared is never 0. We can plug t for 0 and positive and negative value. It's not gonna be 0. So now we move to the second step, second part, which is where is the first derivative is 0. And it's gonna be 0 when the top is equal to 0. So 1 minus t squared equal to 0. I'm gonna move 1 to the other side, and then we'll end up t gonna be equal to positive and negative 1. Now this is our critical point. The second step is to evaluate our critical point in the function f of t. Now notice that our critical points are 1 and minus 1. Now the third step is to determine whether are these critical points a local maximum or local minimum. So I'm gonna use the first derivative test in here, and notice the first derivative test, we want to know the signs of the first derivative around the critical points. So I want to take values that is larger and lower than this critical point in between them, and then plug them in the first derivative, and I want to know the signs. So notice this, the first derivative is 1 minus t squared over 1 plus t squared all squared. So I just select these random numbers randomly. So I selected 0, 2, and minus 2. Again, I'm gonna take these x values and then unplug them in the first derivative, and I want to know the signs on these intervals. Notice in here that the bottom, because it's squared, the sign gonna be always positive. So what we care about is the signs of the top. So when we have x equal to 0, the first derivative is positive, and then when x equal to 2, the first derivative is negative, and then when x equal to minus 2, the first derivative gonna be negative. So now I'm gonna take these signs and mark them on the x-axis. So now around x equal to minus 1, we can see the function f of t. First it's decreasing and then increasing in value. That means it's a local minimum, and then at x equal to 1 the function is increasing and then decreasing, therefore it's a local minimum. Now step 4 is to determine the behavior of the function f of t as t approaches the endpoints. Here we can do that using two ways. The first way is using the graph, and the second way is use the function f of t. So this is the graph of the function. Notice we have a local maximum and minimum here. A local maximum gonna be at 1, and then local minimum gonna be at -1. And the values of these local maximum and minimum are equal, and they're gonna be half. Gonna be half and minus half. Now, on the right side, as t goes to infinity, the function of t goes to 0. And then on the left side, as t going to minus infinity, the function of t also goes to 0. Also, we can determine this using the function of t. Remember, the function of t is t over 1 plus t squared. So as t's go to infinity, we're gonna have infinity over 1 plus infinity squared. Notice the bottom is faster than the top, therefore this term gonna go to 0. Now in case of t goes to minus infinity, it's gonna be minus infinity over 1 plus minus infinity and then squared, and that gonna be minus infinity over 1 plus infinity squared. This is the same thing. The bottom is faster, therefore this term gonna be goes to 0. So now we can see clearly that at t equal to 1, we will have a global maximum, and then at t equal to -1, we will have a global minimum.